here recording a video. Okay, yeah, this is going here. I still have this. Okay, I'm back on the I'm back on what I was doing before. Oh, and I should probably, is it the same link? Let me see if it's the same link. Here's a link. Seems like this is a link. Okay. Every single time I click on the link, every single time I click on, yeah, great. Okay. So, where was I? I seem to be open to the MathLib page on the complex numbers. And I was probably doing something like this. And, this is a somewhat easy theorem, but I think, I probably just need to find the right grind commands to make it work, or ASOP commands or something like that. I don't think I need this lemma. Unsolved goals. Right, okay, so I think I was in the process of this, right? So I had done, basically what I wanted to do was a sequence of things. Here I proved, okay, what exactly have I proven here? I have, well, first of all, what I've done is this. I've proven that the beta integral can be expressed in the form of these gammas. This is pretty much a direct application of this. And it's for general complex numbers, so that's fine. The other thing, so yeah, I think I'm sort of in the process of doing this for naturals, and better than something in terms of all these gamma functions, it would be better if it were in terms of the binomial coefficient. So I think what I want is, okay, so this is, right, gamma is just n minus 1 factorial or something like that. Here, let me double check this again. Gamma, it's either gamma is n minus 1 factorial or 1 factorial, or gamma minus, or one of them, yeah, it's a shift by 1, but in which direction? Good lord, 1 factorial, yes. Other extensions, okay, gamma of x plus 1 is the factorial function. Okay, so if I take that back over here, of x plus 1 is the factorial function. So this is true, probably. Is it true if it's equal to 0? Just let me think through this, right? For gamma, is the gamma defined at 0? Apparently it is not. But that might still be fine. No, it's not going to be fine, because if I take the beta integral at like 1 and 1, it's not exactly going to be right. Okay, but here's the point. So if I take S and T to be natural numbers, and I do something like, I'll just do, yeah, add these two things, and this is not where the colon goes, or no, sorry, this is where the colon goes. The point is that complex beta integral would be this, but instead I can write out using minus 1 factorial. So this would be S minus 1 factorial times T minus 1 factorial, S plus T minus 1 factorial. Unexpected token. Did I not open NAT here? Do I need to like open NAT to get access to factorial notation? Okay, yeah, cool, now this works. So this is all well and good, and I can probably prove this theorem from this theorem by, okay, why is this not working? Because it's not, okay, so I was implying something else. So the point is I can rewrite with this one, and now I have 3 goals, so I can actually deal with those other goals. So I want to do something like have that is true, and I have that is true, sorry, and now I can do H, yeah, so this should just be HS prime, HT prime, that should deal with those goals. And this is true because they're just natural numbers that have been cast, so that's fine. And so now, right, so is there something relating the gamma function to factorial? And that is what I want to know now. So let's go over here, gamma factorial, gamma quotes, factorial in quotes. Yes, this is what it is, gamma nat eq factorial. I might want to rewrite with this in the reverse direction or something. So like simp rewrite using this in the reverse direction, converts all of those properly. So this is a natural number. And now I think I want to do like push cast. with HS and HT. This is now this, and now I can do something like synth, perhaps. Ooh. Yeah, so I'm also going to need HST. Yeah, have HST. Oh, I should also open up the like the YouTube comment section or whatever to ensure that I can see if people chat. I guess that makes sense. Like it's live, yes. Yeah, or whatever to ensure that I can see if people. It's interesting. It doesn't indicate that it's live on the YouTube video, but nevertheless, it seems to be live. So I don't exactly know what the issue is there. Okay, I have HST, which is simply no. This is simply the fact that 1 is less than or equal to bilinear. Bush casts this, and we also want this. So that gets us there. Is this like norm num? Does norm num do this? Yeah, great, cool. Norm num does that. So yeah, so this is now re-expressing this. Yeah, so this is maybe sort of a trivial theorem expressing the beta integral on naturals in terms of the factorial function, yes. And now there's one more way of doing it, which is using the binomial coefficient. So what we could have, right, so if we divide, yeah, so let's do, okay, so number one, this should be like factorial mole factorial. And maybe not like repeat factorial because it's sort of redundant. And there, I want one more version, which is going to look similar. But the point is that we're going to divide not by this, but divide by choose s plus t s. And how does that affect things? So clearly, if I multiply on the top by s and t, I get s factorial. So if I multiply on the top by s, t, and I multiply on the bottom by s plus t, that would get me s factorial times t factorial over s plus t factorial, which would be exactly this. So I think the point is that if I have like 1 over this, there should be a form of this in which I additionally write. Let me just make sure that I'm thinking of it right. I think it has to be s. Yeah, so I have to put s plus t on top. So I have to have something like s plus t times. Put all of this on the bottom. S times t times. S times t times choose s plus ts by. Okay. And now I rewrite using that, sure. It's just telling me that, oh, sorry, I need to come up with a new name. Beta integral equals div choose. Okay, great. So that is that. And so I simply rewrite, and now I just have to prove this big expression is this. And presumably, yeah, so at this point, can I say, please return to nats? It's like exact modcast. Normalize cast and then close the goal with exact. Whoa, did that just work? Unexpected token, expected term. What? Something's not right here. Then close the goal with exact. Can I see an example of this? Is the point that I'm supposed to put a lemon name after here? Foo. An identifier foo. Okay, here, let me like search for examples. Exact modcast. Okay, so yeah, I am supposed to, okay, it would be great if the like documentation would explain that. Exact, I guess it sort of makes sense. Close the goal with exact. So the point is that you have to do something that's formatted like an exact. But it wasn't obvious to me like what exactly it means by close the goal with exact. You're not closing the goal with exact, you're closing the goal with exact like some lemma application. Okay, so the point is that this is just true of natural numbers. So we have that. Okay, well, that's not exactly what I want. What I want to say is I want to copy this out. I say that we have this by, sorry, exact modcast this. Modcast has type, is expected to have type. Okay. Do I have to delete all of these things? I don't want any of these things to be I just want to prove a fact about naturals, right? Right, so this is just a natural number that's being converted to a C. Okay, modcast. Okay, clearly I need to be looking at the documentation for modcast because, like, is modcast the tactic too? Modcast? Just sort of this Frankenstein tactic where I apply two tactics. No, modcast doesn't seem like it's something. Modcast. Okay, why is it put on, I don't really get it. Why does it have mod underscore cast as if it were some sort of declaration? But I don't know like what that declaration is. Can I search for it in documentation? Like modcast. Like if I search for modcast, is there's not like a tactic called that, or I don't know if I really understand that. Modcast. Okay, yeah, I don't get that. Okay, just a second. What am I trying? So I want to have lots and lots of casts, but this modcast has type this, where these are all nats, expected to have type that, where these are all C's. What did I do wrong exactly? Do I have to provide the fact that they're non-zero so that it can put this into this? Is that even possible? Function expect this as termed. Yeah, I don't think that's how that parses. So I'm not exactly sure what I'm supposed to do here. Can I go to the definition of this? Yeah. What exactly does modcast mean? Is it meant to indicate like modulo cast in the sense of modular arithmetic, or is it meant to indicate modulo like modulo the fact that we are casting? Sometimes that's like used. That's like a colloquialism that's used. Rewrites with the given rules, normalizing casts prior to each step. Okay. The point is I have this statement about naturals. Like does hint tell me what to do? I don't think it probably will, but try these. Yeah, no. The point is that I want to like cast. Didn't I figure this out last week? There's some way of like converting like injective cast inj imply. So I was doing it with rationals, but can I do like nat.castinj? Nat.castinj is the definition of this. So I have this. The point is that R is C in this case. So I can do something really ugly. I think I can do something like rewrite like backwards this with R colon equals to C at this, and that will give me that. Yeah, so this is sort of dumb. I can do this again. I can do like push cast at this. No, the issue is that I have to show that this, okay, here's the issue. The issue is that this might be 0. And that's a thing that I have to show. Push cast, wait a minute. After I do this, why does this, I have two naturals. Ah, yes, okay. Let me think about this a little more. S plus t minus 1 factorial is a positive, yeah. Okay, I mean, another thing I could do is once I've done this, I can just say like convert this, and now I just have to do like, yeah, but the point is I have to prove this fact, right? So otherwise none of my logic is going to work. So I have to prove that this is positive, have h1 like 0 is less than this, 0 is less than this. Sorry. The other thing that I have to do is prove that this 0 is less than this. 0 is less than this. Sorry. Push cast. And this is the point at which I would hope that if I would include h1 and h2 in the mix, h1, h2. Sorry, why do I have two goals? I'm a little confused. Where am I? I'm here. 2 goals. How did I get 2 goals? Ah, yes, because I converted. So let's not convert. Let's do this. Let's push cast at this. And now what does this look like? Well, that's annoying. Can I like field simp at this? Field simp? Field simp made no progress. Okay, right, so this is a natural, and this is a casting to a complex number, and I just want the fact that this turns into this expression. Okay, this is yet another sort of thing of me feeling like I'm getting pointlessly bogged down in things that automation should be able to handle for me. So maybe it's best if I just try and move on here and figure out later how to deal with all of these like little points. Okay, so we believe this is true, that we can rewrite the beta integral in terms of this choose thing. And this is okay. So this is to think through this. This is the way I think that we're supposed to prove this statement, right? So let's see if I can use this fact here that I'm asserting in order to prove this statement. Okay, yeah, but clearly I actually need some additional things, right? So I have these two things. And the point is that these are casts of natural numbers. So yeah, these are casts of natural numbers, and these are probably complex numbers. No, they're rationals. What? Okay, so this should be a complex number, right? This whole thing should be a complex number. And at the end it becomes a complex number. Okay, complicated. So what I should do now is I should try and yeah, let me think of this. The thing is, I wonder if I've done something sort of equals div choose. Yeah, the thing is, what I've done here is I've formulated it in such a way that it's a nat cast like directly in the theorem statement, which will make it like hard, like, because I think the problem is like how did I get to the point where I have this, and the thing is it automatically turned this like you can see what I wrote here. These are all natural numbers, but I applied it to complex beta integral. This argument is unused. Okay, so what I want to do is, yeah, so this is what I want to do. I want to rewrite using this fact. The values of S and T that I want are M and this. So I want these two values of S and T. Rewrite failed. And the problem, okay, I have to do it backwards maybe. Maybe that's the issue. Rewrite failed. And it's going to say, okay, wait, no. Let me focus. Where is it? Beta integral div choose. This is the lemma I want. Complex beta integral div choose. Yeah, okay. And this is the issue, right? The issue is that this is not cast, whereas this is cast. Somehow it's automatically cast, which is frustrating. Like in the process of writing this, yeah, I mean that's just sort of I don't know like why that happens. Why is it that when I write complex beta integral, these are natural numbers that I gave here. And what I want to do is I want to say something like, yes, this is a natural, but I want you to only cast it later. I only want you to cast it like this. And now it works, right? Unsolved goals. Of course, now this, so now what I have to do is like push cast at beq to get it back into the, no, does that not, what happened? Yeah, okay, so one issue is that I have a conjunction in my lemma statement, which is maybe not something I should be doing. So maybe I'll try to fix this first, because this is not like writing it with a conjunction like this is not HMN. It's not how it's supposed to be done. This is no longer h.write. It's something that exact will know. And push cast. So clearly I need HMN. And now that it should be sort of back in the state that it was. Okay, actually now, no, it's actually not going to be in the state that it was, because now I have pushed this through into complex numbers here. What am I proving here? These are statements about rational numbers or complex numbers. Yeah, these are rationals. Yeah, super frustrating. Okay, so I have to think through like what I did wrong here. So I have these rationals, and maybe the point is that I should just rational is integer of exists integer. So I could convert this thing here to be about complex numbers, but I get nervous that am I not doing what I'm supposed to be doing at that point? Maybe not. Let me try and recall what all of this is doing. Did not find an occurrence of the pattern. This equals this in the target expression. Yeah. So I have this. Maybe Maybe I just need to not do that. This is a C. This is a Q. Cast inch. Can I rewrite this at the goal? Cast. Okay. Well, this is okay. This is a rational. This is the shoot. R equals C is what I need. R equals C. Invalid name for R. Alpha. It's called alpha in this case. Okay. Alpha equals C. I can now push cast. This is a casting to C of a rational. So I can also hopefully push cast at this, or no, at BEQ. Exact BEQ. Okay, so now that is proven. So now this statement is still about rationals, right? So I can rewrite with this, and I'm still in rational land. Yeah, okay, great. Except that now I have to QFI. So QFI, this is, so all the H's became HN and HM and HMN, right? So this should be, all the H's are now HMN, HM, I guess, both of these, so that's fine. Unsolved goals. It's so hard when like the unsolved goals makes it like you can't see what's going on. Why does it say that I have unsolved goals here? So I simp at this, I replace, yeah, so that gets, I do some replacement. Now I have HK. I do this at HK. Do I even need this? Yeah. And I don't need this anymore. QFI at H. Yeah, okay, cool. Now the rest of the proof compiles. Or does it? Oh, yeah, I need, okay, the issue here is that it's just like, I haven't put a lemma on this, so I'm gonna comment this out. Okay. And what's the red thing here? Okay, there's unsolved goals here. Yeah, so this is what I was in the process of doing. So it's mn minus 1, and I additionally need various proofs. So this is going to be HMN, or HM, and this is going to be bilinearith. Great. Cool. So that gets me here. Yeah, so this is a Q, this is a C, these are probably C's. Yeah, so now I want to like push cast with everything. I want to push cast. Yeah, this thing is definitely positive. I want to push cast. I have a whole bunch of things that are positive. Is there not like some way of like doing like plus? Please use positivity to do this. Like, please just discharge my goals for me. Like after I do push cast. Okay, wait, no. Did progress get made here? Let me see. Yeah, no, sorry. Progress did get made. So now this is a C. Okay, I see what's going on. We're very close to having it all working. Let's try push cast with the HMN. And let me see. Okay, clearly the issue here is that I have n plus n minus m plus 1, which should just be n plus 1. Is that even right? Just a sec. These two things are the same, so they should cancel out, and I should be left with 1 over something choose m, but I seem to be off by 1. Did I mess something up in one of the earlier proofs? Oh no. Because this has a plus 1 in it, and this does not. Let me look carefully. Let me try and look carefully at one of these other things. I'm worried that I'm worried that like one of these statements is wrong. Okay, I guess I just have to try and clear the sorries here just to like convince myself that I did everything right. This should be a linearith, right? Linearith, because it's real. Okay. Can I simp? Shouldn't it be possible to simp? Yeah, simp. Okay. Copy. Paste. Okay, so that at least is true. And now the question is this not true? The point is that this should equal this. Positivity works. Cool. Let me just like clear these. Copy. L positivity. Why? Strict positivity, but would be possible to prove non-negativity. Why? Just a sec. Strict positivity. Okay, I see the issue. The issue is that this can possibly be, I understand. How do I know that this is not 0? It's because s plus t is greater than or equal to s, but that is a fact that is beyond the scope of positivity. So what I simply need to do is I need to first prove that have h2 prime 0 is less than this by simp nat.choose pos if. Okay, I feel that there should be something like this. Should there not be something like choose pause? Yeah, but is this not an if and only if? I feel like maybe did I encounter this before? I might have encountered this encountered this particular point of confusion before. That this is like, it feels like this should be a simple enough. Nevertheless, I can apply this. So apply. Great. So that works, and now positivity works here. And now we have something like this. Right, choose. Okay, so can I, add a choose is like, right, add choose, or maybe nat.add choose. Yeah, this one. Did not find an occurrence of the pattern. What? You didn't find it right here? I need, sorry, I need I need it to work out differently. It's probably like add choose prime or something. Okay. Go to definition, add choose. Okay, this is clearly what needs to be done here is we just need to have a add choose right, add choose left, and a whole bunch of other things, because I would like to be able to say that I plus j choose j is the thing that I'm looking for. Okay, so let's do that. Dot add choose prime, choose I has this property by sorry. This is add choose prime. This is proven by, sorry, this is nat.add choose ultimately, right? Yeah, right. Nat.add choose. Or no, what I need to do is I need to rewrite add com nat.choose. I think I can just do add com and then add choose, right? Yeah, cool. So that's how that goes. And so what's my state now? I have this, this, are these C's? Yeah. Wait, what? The point, sorry, I shouldn't be doing this here, really. I should be doing it up in the proof of here, and the point is that I'm so close. I'm so close. I've rewritten this at this. I still sort of want to like convert. Okay, so I feel like this maybe goes up here, and what goes down here is convert this. And now I have a whole bunch of separate goals. Push cast. I want to like push cast. Sorry. Doesn't do any, or does it do something here? I was doing this before and I'm not experiencing progress, but I want to push cast at this and turn this statement into, what have I done here? Sorry, I'm back here. The point is that these basically match. The point is that this is this. I have H2. The point of doing H2 was so that I could do something like push cast H2, but that doesn't apparently work. Is it normcast, pushcast? It can be used with extra symplemas. Add 0. So I need to like know the right symbol. See, also normcast. What's the difference? Normcast. Family of tactics normalize certain coercions. Simp with a specific set of lemmas to move casts upwards in the expression. Non-terminal simp calls are discouraged. Normcast is considered to be safe. So what does this do? It moves it up the tree. Okay, that's something more like what I want. Can I do more normcasting here? Like normcast. What happens? I have this and this. Why is it not being able to figure this out? Shouldn't there be like a exact for this or something? It feels like I almost have it here, right? So this is a natural. That's the issue, that this is not a natural. Like this is a natural, this is a natural. Oh, am I doing natural division? Oh, shoot. Is this a natural division? Yeah, it's a natural division. That's annoying. Okay. In some sense, okay, the problem starts up here. No. The problem starts here. The problem starts here where I have these natural numbers. Ugh, yeah, this is not easy. This is where the problem starts. I sort of want them to be rationals and not naturals. So for example, I could put a rational type ascription here. This would become a rat cast ing. And we figured out that this was alpha. So now I'm here and I do norm cast. This is a rational, but it's fine because this is also a rational. This is the C. Let's see. This is a nat being cast to a C. Like, what happens if I push cast here? Push cast. How does this look? Okay. This is so weird. This is being cast to a C. This is being cast to a C. This is being cast to a C. This is an okay. This is a nat being cast to a C. Are these equations not identical? It's just like roughly. Okay, cool. Interesting. And I guess my other question is, if I were to do all of this before the conversion, would that work too? This. Okay. Yeah, never mind. I'm just going to try and do it the hard way. So I had this. I norm cast this, and now like push cast and ruffle. Okay, no, it's been so. Clearly there was some easier way of doing it, probably. Like, instead of converting this, I should do something else. Okay, but I have one more. So this is, okay, the whole point of doing this was so that I would not screw up this critical part. So am I not screwing up this critical part? So these are now rational numbers. Yeah. I want to do something like field simp. Can I do that? If I'm doing rational numbers, I might be able to field simp. Okay. Well, you sort of didn't actually get rid of all of the field simps, did you? Like, what is that about? Field simp to reduce an expression in a field to an expression of the form n over d, where neither n nor d contains any division symbol. Liar. This is a form n over d where d contains a division symbol. But it's a natural division symbol. Okay, wait. Am I insane here? This is q. Wait. Did I not fix? So this is a q. Okay, wait. Just a sec. This is a natural division. How is there still a natural division here? Add choose. Oh, did I do add choose having a natural division symbol? Does the original add choose have a natural division symbol? Oh, okay. Yeah, this is sort of annoying. Okay. Yes. I don't know. This is like time for my like searing hot take here, but MATLAB should just like totally rewrite its entire hierarchy to eliminate like truncated natural division, because it's just a bane on my existence. Okay, so this is nat.addChoose prime. Why don't I make another like theorem, which is like rat.nat.addChoose prime, rat.nat.addChoose prime, which is simply to say that if these two things are natural numbers, and I take this and I cast it, in fact, to a Q, this will now turn into a statement about rational division, which I will sorry out for now. And now I have rat.nat.addChoose prime, and I can rewrite using rat.nat.addChoose prime, and then I can do field simp, and now I won't have that issue. Okay. Yeah, funny. And of course, the critical thing is that we have to know that it actually does divide. Yeah, that's interesting. But anyway, so this is just a story that I'll leave there. Okay. This is where you could probably do some like wizardry here surrounding the concept of like successors, right? Like because the point is that we have like s factorial, we have a whole bunch of facts, right? Let me just like look at this. S minus 1 factorial, S, that gets S factorial. T minus 1 factorial, T, that gets T factorial. S plus T factorial. S plus T minus 1 factorial, S plus T, that gets S plus T plus 1 factorial, and we have S factorial and T factorial. So I could do a lot of unfolding of like S would be S prime plus 1, and I would like substitute all of those in, and I would unfold the like successor of factorial, and then I would apply ring, and I think it would be possible to prove this. So the point is, okay, so returning back to my confusion, popping up some number of levels of the stack, the metaphorical stack in my brain, I think that this is a correct theorem, which leaves me with the question, what is going wrong here? Because I had applied that theorem, and I was here, applied that theorem here by Linnerith, and I had this. Okay, yeah, something was not right. The thing that was not right and that was confusing was, okay, maybe this is all much better than I thought it was. Let me just think this through, sorry. So I have this. This is complicated. This is a choose expression. The point is, this is m plus this. This is a choose expression. This is a choose expression. What we really need to do is like what would be cool? Yeah, positivity bound or something like that. Like positivity extension. The thing is, I don't know if this can be done, but like a positivity extension to prove the positivity of these choose statements. What should really be done, right? Like in some sense, what should really be done is that the natural function. I don't know if I like was expressing this last time I was streaming, but I was definitely thinking that in some sense, choose. Like if I go to the definition of choose, it's a function that takes two naturals and returns a natural. But in some sense, the much more like nat.multi-choose is actually the much more natural notion. Sorry. Well, no. What is this? No. This is not what I was thinking of. Multi-choose. Multi subsets versus multi-set. No, this is not what I was thinking of. That's actually so confusing because okay, here's what I thought, right? I thought that multi-choose would be, choose is for the binomial coefficient, and I assumed that multi-choose would be for the multinomial coefficient. But that's not what's going on here, I think. The number of subsets of cardinality k from a type of cardinality n is the number of multisets of cardinality k from a type of cardinality n. Yeah, that's not what's going on here. This is all to say there should be a function for the multinomial coefficient. Let me see if I can search Linux for multinomial coefficient. Multinomial. Nat.choose.multinomial. Let me take a look. Multiset.multinomial. Yeah, this is looking right. Nat.choose.multinomial. It has a fin set of alphas and a map from alpha to n. This is another case where it's like, okay, we did this indexing trick with fin set, but it would be so much easier if it were just a multi-set of n's, right? Yeah, I don't know. This is maybe too much of a computer science way of doing things, maybe, but it would be very nice if I could just express I could produce a multiset, like a function from multisets of nats to nats, which is the multinomial coefficient. And anyway, it would be very nice if I could have a version of the choose function which has this other property. I want a choose prime function, which is equal to choose n plus k. We have this choose sim, but it's not actually a sim function, right? Usually sim theorems are theorems of the form x of ab equals x of ba. That's not what's going on here because of how it looks. Yeah. So what is the secret? Nat.descending factorial, right? Yeah. Naturally. Compiler simplification theorem is fun. Okay. Well, where was I? Yes. Okay. So this is actually a somewhat complicated expression involving lots of chooses that I don't know what to do with. Maybe my instinct should be to immediately convert all chooses into factorials, just so that I can adopt the pattern of always going to factorials and field simping and all of that. In which case, maybe it was not the best to actually write things this way. I guess one critical fact, yeah, basically all of this weird number theory is it's somehow very, very conducive to short number theory proofs to use the fact that n choose m is an integer, and also know that it has a certain divisibility property. It's very conducive to be able to say that n factorial times n factorial is or divides evenly into n plus n factorial. And that's just sort of this strange fact that happens with the Bertrand's postulate and also seems to be happening with this proof. Okay, so maybe this proof is actually right, and I just need to focus on how I'm doing it. So yeah, we've got a lot of stuff here. Yeah, we want a field simp. We just want a lot of things. Yeah, the thing is, I basically just want a version of positivity where I can use the fact that I know that this happens to be I want a version of positivity that goes into the question of certain bounds, and so it goes into the fact okay, can I prove that m plus n minus m plus 1 is greater than m, then it like turns that into a fact that it handles. But I think that's just out of scope for positivity, I guess. Atoms composing the expression all have numeric lower bounds, which can be proved. Positive slash non-negative slash non-zero by norm node. This tactic either closes the goal or fails. So it's like a terminal tactic. Yes, max. 0 is less than max can be proved by positivity. Okay. So yeah, what has to actually happen? Can I just do like field simp? Yeah, okay. But yeah, let me like run through that entire like train of thinking, because the whole reason I was on that train was I was thinking like, okay, if I could just have a version of the choose function, which I knew was always positive, what I'm tempted to do is like come up here and say something like def nat dot choose prime. And this will be like A, B are naturals, and it returns a natural, and it's equal to nat dot choose A plus B choose A. Alternative form of expressing this is an alternative form of expressing binomial coefficients conducive to positivity. And the point is that theorem, okay, cool, I have this definitional theorem. I have choose prime sim, which is that that is true. Great. No, I didn't get it quite, but okay, but it's obviously true, so I'll just say sorry. And like theorem, choose prime pos. Yeah, great. Avoiding subtraction. It's conducive for many reasons, right? Like one reason, it's conducive for positivity proofs, avoids natural subtraction. Subtraction is what it avoids. We still have natural number division, of course. Sorry, what was the proof it tried to produce? Like choose equals choose. Yeah. This is the thing where I feel like it should be like rewrite question mark, and then I can choose sim add. Yeah. Rewrite addcom. Yeah. Okay, cool. This is a correct proof. Anyway, so I have this nat choose prime, and now the key is to rewrite everything in terms of it. Do I need to like, is there something I need to do in order to make the positivity here? Is the chat working for those who are logged into YouTube? I see that someone has actually been commenting on this on here. Let me see if I can chat. Chat, is the chat working for me? Seems like it is. I wonder if it's working here. Let me quickly grab this and open it in a incognito window to see if it's working. Okay, but obviously, sorry, I'm not actually going to be logged into YouTube if I do that. That's unfortunate. Yeah, what if I like use a different Chrome profile? So Chrome, new window, I go to like a different Chrome profile, and I try this, and I try this. Okay, so this is, no, actually it seems like I'm not. This is annoying. Okay, so yes, clearly everyone who is getting on Aaron Liu's case in the comments yesterday had no idea that just the chat was not working at all. Okay, what is actually the issue which is causing chat not to work? Here, we're turning this stream into like a technical resolution. Enable chat YouTube live stream. Sign into YouTube Studio. At the top right, click Create, Go Live. Okay, well, I already am live, so that's a little concerning. Select, okay, yes. Under Customization, check the live chat box to turn on live chat. Sign into YouTube Studio, top right, click Create, Go Live. Yeah, this is what I'm doing. Stream settings, maybe. Okay, no, there's actually nothing here. Add channel URLs to the approved users list. What is this? Yeah, I cannot chat in live streams. Help. What is the issue? Yeah, I don't know what the issue is here. Use live chat. Okay, this is not very helpful. All right, I don't think it's the issues that I said it's for kids or anything. It's definitely like not for kids. So that's the incantation you give YouTube to say that it's fine. Participants, yeah. Okay. Yeah, I think perhaps the best way forward is for people to just chat directly on the like the Zulip on Zulip rather than YouTube if that's what's because I like I agree that it seems like I can't use a different account to make chats on the live stream while it's happening. Um, and I don't know what the reason for that is. Clearly, YouTube needs to make it easier to do that, but um, yeah, I guess that's what it is. Okay, returning to writing link code. Okay, so nat.choose prime, which I am defining now. Do I have to do anything to make it possible to use positivity right? Let me like go down to the positivity tactic. Okay, like test, lemma, pause, like, okay, test. The test that I'm doing is to say that nat.choose prime 3, 4, 0 is less than this by positivity. Failed to prove, yes. Would be possible to prove non-negativity is desired, clearly, because it's a natural, but that means it's not working. So what do I need to do to make it work? Clearly, this is what I need to go to do. I need to go look at this and say, like, is there something I have to like tag with positivity extension. Run each registered positivity extension on an expression, returning a norm num result. Yeah, so I have to write like some kind of extension. Is that what I'm being told here? I have to like, is there not just such a thing as like at positivity? No. An extension for positivity. Structure positivity ext. Okay, clearly I should be able to like look at other things and how positivity. Okay. Okay, well, I spelled it wrong, but unfortunately, this is just going to give me a bunch of uses of positivity. What I want is an example of how at positivity. What is this? Okay, extension for the positivity tactic. Yeah, this is sort of what I want, right? But I don't know how to do it without the positivity extension, which identifies expressions of the form absolute value A. Yeah, it would just be nice if instead of having to do metaprogramming to get the tactic to work on my new definition, I just had to like tag it, right? And maybe that was how it worked at some point in the past, but like at posit. Oh, wait, maybe it does work this way. Sorry. Attribute for identifying positivity extensions. Okay, but the point is that this is like some weird metaprogramming type rather than just something I can apply to a lemma. Or is it? Here, let me just like experiment. Can I say like at positivity? Expected term. Unexpected type. Yeah, so it has to be positivity extension type. So what do I like? All right, metaprogramming time. I need it to be a positivity extension, which is something like this. What is a positivity ext type? I need to do like section meta, section positivity extension, or positivity extension, and yeah, okay. I guess I should also say with respect to comments that they are not working and that people can feel free to type things in the in Zulip. Not sure what the issue is. People can comment here. There we go. Positivity extension, and now I need to write. Now I need to write this. Okay. MATLAB meta positivity of okay. So this is okay. So where am I? I'm here. I'm looking at an example. I'm looking at like the absolute value. I'm looking at an example. Yeah, absolute value. Wonderful. Absolute values are positive. And this is how they make it a positivity thing, which is, okay, they first open a whole bunch of namespaces, and then, okay, let me just like copy this, right? This is me doing metaprogramming. It involves copying and pasting, working things, and changing until it works for me. So, lean meta mathlib meta positivity, QQ, positivity expansion, which identifies expressions of the form choose prime AB, AB. And so here we have positivity extension. Let me go to this again. Positivity extension is a structure which has a has a single field eval, which takes a whole bunch of weird metaprogramming stuff. Q0. Okay, yeah. So clearly, yeah. Okay, yeah. So this is all stuff. I think what all the point is, all of this stuff is stuff associated with the fact that the type I'm proving positivity for has to have like a zero type class and a partial order type class in order for positivity to make sense as a concept. So that is all fine. And if I look here, yeah, okay, so positivity X, where eval, okay, so eval, sorry, let me look at all of the things. So eval has let me just see if I can recall, yeah, the type is like certain types of lean expressions, right? Okay, so I guess it has a universe level, great. And in the case of absolute value, are those, yeah, okay, so it has two implicit things, which are the universe level as a lean type. Of course, this is confusing because it's like universe levels are not like types, but in the case of like oh yes, we are representing lean, and we actually have like a type of lean levels. Okay, probably isomorphic to the nats or something. So this is an implicit argument, and then an implicit argument alpha, which is simply the type, probably the type that I'm working over. So in this case, it's probably nat. In the case of absolute value, it was this underscore alpha thing. This is the zero. This is the partial order. Okay, yeah. I wonder if right. So the point is I'm going to have to throw, okay, yeah, fine. So I'm getting an alpha, I'm getting a zero condition, I'm getting a partial order, and I'm getting the expression of the type that I have, which is supposed to be, so the point is I have to start throwing errors if it's not of the right type. So what I think I have to do here is, so F, what is F here? F, what is F? F is an expr. Where does that come about? Yeah, like this, F is an absolute value. So I guess F is the thing that we're proving is an absolute value in this case. So oh gosh, why is this so complicated? WHNF with the reducible transparency. Throw error, not absolute value. Yeah, so I want to do something similar. Yeah, so I take an expression and I get a meta expression. So this is what's happening here. This is like a pattern match, maybe? Is that what this is? Yeah, I think this is a pattern match. So, okay, this is gonna I'm definitely gonna screw something up here. I'm matching this. I think what's supposed to happen. Right. Okay, but it's a little complicated. It's complicated by the fact that this is a two-argument function. That complicates things. This is a two-argument function. So it's it would be better if I had a better example. Is there another example of someplace where like this substring occurs where I can maybe like find an example of a positivity for something like this? Inset.prod, maybe, but can I get something even simpler? Real.x, positivity, hsmol, something like this. This is maybe good. Yeah, something like this. Okay, this is interesting because it has a very explicit expression. So maybe this is the expression I'm supposed to be matching. So that would indicate, yeah, okay. So this is looking better, and it's got type descriptions here. So if let me try and like copy this. So I can try and copy this. So again, it's creating this positivity X thing. Okay, yeah, something like this. So instead of this exponentiation thing, what I want is nat.choose. Something which is a natural number, something else which is a natural number. There's no thing anymore, so it should just be expressions that look like this. And this will be eval. Okay, I guess the right name for it is something like eval choose prime. I'll choose prime. The positivity, identify those expressions. Yeah, okay. Positivity expression, universe level alpha, the zero, the partial order, the expression. I match universe level alpha expression with, okay, and this is where I have to do. Yeah, clearly it'll throw an error if it's not nat.choose. But the thing that I need to match, okay, so clearly this is not nat.choose in some cases, but the thing that I need to match is I have u, yeah, okay. I think the point, yeah, just to like think this through. I think nat.choose is in universe level 0. Like if real powers are in universe level 0, I think this should definitely be in universe level 0. So I think I'm right to say the universe level should be universe lean level 0. That's fine. This, the alpha that we're doing this for, I think has to be nat. And the expression should be, okay, of course it's this weird, this QQ thing, but the point is that it should look like tilde Q, nat dot choose prime, $A, $B. Yeah, just to get it in my head, it should look basically like this nat.gcd thing. It should look like tilde Q, nat.choose prime, $A, $B. Nat.choose prime, of course I need to spell it right, $A, $B. I don't need this other type description stuff, I think. And the point is that, okay, so if I have 0QN, choose prime, $A, $B, now I can proceed. Yeah, and I can always look back at how it looked, right? And I had a $A and a $B, and here it like seems to be able to use the A and the B. Let RA equals core Q infer instance. Okay, so this is positivity core. It runs each registered positivity extension on an expression. Okay, so this is actually sort of maybe a little bit of a weird positivity, in that usually when you call positivity, you need to prove that the sub-expressions are positive. But in this case, I don't, because I'm pretty darn sure that choose prime is positive literally no matter what you do. So what is supposed to be returned here? The point is I need a meta m. Is this strictness? Infer instance. What is it inferring exactly? I don't assert instances commute. Match RA. Okay, let me think. Non-negativity. So clearly it should be able to prove both positivity and non-negativity. Maybe it doesn't need to prove non-negativity because it's already a nat. Maybe. Yeah, I don't. I'm not exactly sure. So okay, I'll get rid of match RA. Okay, I just need to read carefully what this does. Run each register positivity extension on an expression, returning a norm num result. Q of A, right? So Q type U is the type of expressions of type U. So that is automatic. The 0, can I just do something like tilde lowercase q nat.inst0? Maybe? So I have the 0, I have the partial order, and then I have the expression of type alpha, which is just, oh, yeah, sorry, let me look back over here. Well, no, let me look here. Sorry, where was I? Was here. I have alpha. This is the recursive when the base is non-negative and positive when the base is positive. Okay, so the point here is that I'm recursive, like the point of this, I think, is to recursively go. Is there another example where I don't have so much stuff? Like, okay, let me think of sine h. No, let me think of cosine h. Do I have an example of cosine h here? Yeah. So this would be an example of a function which is always positive. And all that I do, okay, so I literally have 0, real.cosine h a. Apparently I need to write assert instance. So this is an even more accurate thing, perhaps, of what I need to do. I don't need this. I just write assert instances commute, which I don't know what that means, but that's what seems to have been done here. And I write return dot positive q nat dot choose prime pos. Yeah, so nat dot positive q nat dot choose prime pos $A, $B, presumably. Great, and now it works. Oh, goals accomplished. Wonderful. Okay, yeah, it's interesting. We even have this meta m thing. Yeah. Okay. Yeah. I mean, Aaron brings up a good point that maybe this is not a good. Yeah. Should I try and get this comment thing to working? Oh, actually, someone did manage to comment. Rita Hamadani managed to comment. Okay. Clearly there's not actually an issue. Maybe I am mistaken about it not being possible to comment on the YT chat. Okay. Well, I think I don't necessarily have to worry too much about that then. Hello to the viewers. Okay. So I've made this positivity extension. I'm in the process of doing this, and now I'm in the process of like rewriting my entire proof using this more natural notion. Yeah, nat.add choose. And so one way that this could all be rewritten is to say that this is choose s plus t s. Yeah, okay, interesting. So yet another way of writing this theorem would be eq div choose prime, and I would replace choose with nat.choose prime s comma t. This would be a sorry. And so now I have beta integral div choose prime. Very cool. And now the question is, if I like go here and add a prime here, I can do this. And now I'm doing this here and this here. And if I do field simp, does it work? Okay, so yeah, like moment of truth, does it actually work to do field simp here? And I guess maybe the answer is not no. Because I still, okay, so number one, I still have a choose here. And let me like rethink how I'm writing all of this, right? The optimal way, yeah, let me think through this. Sorry. So if I were to rewrite this thing that I'm proving in a way that was totally equivalent, but just to use choose prime instead of, so the point would be that instead of n, I would have, okay, so like the guide is that n is going to equal m plus k, I think. And I think I'm going to write, so there's going to be, instead of n, there's going to be a k. 1 is less than m, and because, so m is less than or equal to n, so this would be n, like m plus k. And instead of n dot choose m, it would be nat dot choose, okay, so it was n choose m. So now it's just going to be m and k, and this is m plus k. And this is choose prime. So this is a way of writing it without any reference to n. And I can add back in the reference to n to get things to work. So I can do something like let this suffices, yeah. But actually, even better than doing that would be to not do that and write things in the way that is a little bit better. So the point is that choose n becomes this. LCM n becomes LCM n plus k. All of that still goes through. So let me like remove this, and presumably I will encounter errors down here. But now I can continue thinking, right? So, oh, wait, what happened? Interesting. Okay, just, yeah, like n plus k. So yeah, wonderful. Okay, yeah, first order of business is to put this in parentheses and replace literally every instance of m with this. No goals to be solved. Great, that's cool. Let's keep going. Right, this is the, yeah, systematically, just very slowly and carefully rewriting everything. Delete this, a bunch of m's, all become m plus k, and now later I can rewrite it all. And all of the proofs still go through because all that really happened. Now this, sorry, did not find an occurrence of the pattern. Yeah, because, right, I understand. It did not find an occurrence of the pattern because I changed some other things. But still, the n's become m plus k's. And the point is that the m plus k minus m is just equal to, in fact, k, because that is how math works. Okay, wait, what just happened here? Oh, shoot. Wait, do I have another use of k? Ooh, yeah, I introed k. Just a sec, let me go back. I feel like this should be undo. Yeah. So before I do this, this should be J, this should be J. All the K's here should be J's. Just switching index terms. HJ, HJ. Yeah, so that looks right. And now I can replace the N with M plus K. And I don't know, so clearly something is still going on with the the choose function here. I don't know exactly how I got back into that, but okay, so the point is that this, okay, now let us rewrite. So all of these can just become k. I don't have to worry too much. Clearly I'm using a lot of k plus ones. Oh, shoot. I need to undo that again. Sorry, I chose the wrong, I chose the wrong, the like index because I was like using k everywhere and then I decided to like blithely use k. So I'm just gonna undo all of this so that I'm closer to where I started. And this was n, okay, so I'm back where I started. Let us say that n equals m plus j, or n plus foo, wonderful. I love the ability to rewrite with foo later. So this is this. I'm not gonna have an m, I'm gonna have n equals m plus foo. So this is m plus foo, wonderful. Writing this code, all of the n's become this. Just writing a bunch of these, all of this gets commented out. Can find an appropriate thing to replace foo with later. Okay, we can still have that be k, that's fine. Don't need to change that much. Fail to find a contradiction. That's sort of interesting. Yeah, because, okay, and presumably that will actually be fixed by the thing I'm about to do now, which is to take all of these and turn them into foos. Oh, wait. Did I not fix everything? This should be that. Yeah, okay, so that's all the ends. That's fine. All of these just become foo. So that can turn into foo. And now, and there's further things to be done, which is that all of these should become nat.choose prime m foo. And positivity. Maybe it could be. That's one way of solving that. Okay. Yes. Well, Mars has managed to join. Hello, welcome. Wonderful. Okay. All right. So that has changed. Okay, we've made a large change, and now we have various things. But it should be much easier for positivity to prove things now. And I failed to find a contradiction here. Why did I fail to find a contradiction? Do I need to like push cast first or? Yeah, okay, interesting. Okay, cool. So I'm going to proceed. All right, the whole, yeah, so wonderful, foo. I should probably choose a better name for foo, but yeah, it's like the difference between these two things. And okay, so here's like another comment, which is that foo, like I don't actually need HMN here because this is just a statement that foo is positive, so I should be able to delete this and like remove this and remove this and remove this, and things should still be okay. Okay, cool. A little golfing got done there. Okay, great. So now I'm here with choose prime, and I guess like another key. Yeah. So okay. So what happens here? I do this, and I get these expressions. I guess field simp. This is positive, and I feel like I would like. Okay. So does field simp uses positivity? We'll try among other things positivity and norm num and try to prove things are non-zero. Does field simp by default, like the thing that I really want field simp to do here is put these denominators on the other side. Is it because I'm casting? Maybe. I'm dividing by this, but it should be possible. M is definitely positive, and M choose prime is definitely positive. So all of these things are positive, and it should feel like comfortable. It should be possible. Okay, here, let me think a little bit more. There should be a theorem. Okay, to fill out the choose prime API, there should be something like theorem nat.choose prime equals some equals factorial. Right, that's true. Okay, choose equal. What's the nat.choose? There has to be something in terms of factorial for this. Choose eq factorial div factorial. Yeah, that's so. What we want here is choose prime equal factorial div factorial ring and field simp. Field simp did not make progress. I guess because I don't actually have a field here. Right. But I can maybe just like simp here. Can I simply simp because it's so close, right? Simp. Okay. Okay, that's interesting. Yes. Exact. Yeah. Okay. Cool. So this is how I rewrite, and starts with two goals. Wait, just a sec. Starts with two goals and ends with one goal. Ah, okay. This required a lemma, which is okay. So simply, I will say by exact question mark here, and now I will not have to deal with that. And it doesn't even have to have a by exact here. Okay. Cool. That's great. So I have that theorem. And there's an open question of like, is this theorem really better than nat.choose like the rational version of this theorem, where I say like a rational version of nat.choose AB is these numbers as rationals divided by each other, because that way I tell it that I'm not like truncating division or anything. So looking again at where I was going to use this, yeah. So yeah, this was the okay, so haha, nat.add choose prime. So this is not something I'm going to use anymore because, yeah, so I was going to use it here, right? So rat.nat.add choose prime. So let me see. The point would be to do something like to take this and do, and this is not like a good namespace, but the point is that if I have this and I like convert it to a rational, in fact, this whole thing remains true. And I'll leave it sorry for now. So I have this, and maybe I can use it down here somewhere. I can maybe do like this. Oh, something's not quite right here. Yeah, sorry. The point is that this is the old. Okay, sorry. The point is that this is the old one that I don't need, but which is still maybe like useful. Here, let me like make a junk file or something. Junk, that might be useful later, but I don't want in my thing right now. So this falls into that category because it does not use the new choose prime function that I have created. So that can go there. Beta integral, okay. So yeah, everything is in terms of the choose prime function. So we have this, and we believe that this is true. Yeah, we're pretty confident this is true. So we're just gonna like express things in terms of this. So what was I doing? Yeah, I have this and I'm moving along. I'm doing field simp and it's doing this, and I want to do something like simp simp only this. Okay, wait, are they rationals? What are they? They're C's. Yeah. Yeah, I don't know, like clearly I should know what the best way of moving forward is here, but I don't. Just having a lot of these, like, okay, I want to turn this into something. Yeah, it's just like an interesting phenomenon where I have this thing in the complex numbers. The fact that it is, I want to prove it for like, not for the complex numbers, or for have it for rationals. Like what I could do is I can like make yet another version of this theorem, which is complex dot all of this. And now, so this is a complex version of the theorem. Now I can say something like complex, not this. And now, simp like only with that maybe. Now I have a bunch of things. Now I can do field simp, and now I can do field simp and low. Wait. And now simp. Yeah, but now, so the thing that I sort of want to do now is I have this, and I actually have a bunch of factorials with additions, right? So I want to do like factorial suck. Nat dot factorial suck. Like, where does that get me? Does that extract? Yeah, so I managed to extract, okay, but I didn't manage to do it here. So I also want like add a sock. No, I want it backwards. Something like this. And this gets me here, where as far as I can tell, all of the things have been removed. So now I have this. Yeah, so I'm multiplying this. I have m plus foo. Yeah, so I have m plus foo factorial, and I have m plus foo factorial, and I have an additional factor here. But the point is that it's supposed to cancel out with this. And now I think I have, right, m foo plus 1, m factorial, foo plus 1 factorial. So this seems like it's correct. Okay. So I'm feeling more confident about this, and maybe I should try and move on to like a different sorry. So I guess the point is this one. I feel like, unfortunately, like I feel like I haven't made any progress because the whole like this is the like the this is where things are actually supposed to start to get difficult, not all the rest of this. Things where the way that this is supposed to start to get difficult is that I'm actually supposed to be able to prove this particular theorem, which was supposed to happen by integration by parts. Or no. This is actually not by integration by parts. Like if I go to the beta integral, what is this? Imports are out of date. Yeah, so I have this expression for the beta integral. Beta integral scaled, yes, equals this times beta integral. Okay, the point is that we have a recurrence for the beta integral, sure, but what we don't have is like this formula, which should itself, yeah. So the point is, partly the point of this is that this seems like it should be oh, we actually have a choose here again. Interesting. Ooh, choose K. Yeah, the point being that K never gets above foo because we have K in finset range foo. So I'm not exactly sure. Like my hope is that at some point there's some way of extracting this choose thing. But the point also is that this should be its own lemma, right? I should have like beta integral equals sum. Let me go and try and do that. So yeah, like a lemma with the other beta integral lemma. So like lemma complex dot beta integral integral equals sum. I wish there, like clearly it's impossible. Yeah, this is sort of what I want. I'll have to double check that. I wish there was some way to make the Copilot leave the sorry and only like stop generating on sorry. I wonder if there's a way of doing that. But of course it never like produces the sorry, right? So complex beta, and probably because it's been trained on too many things that like don't have sorries in them. Complex beta integral equals sum. Yeah. So yeah, scrolling down here, right? What does the thing that I was going for look like? If I have natural numbers m and foo, then if I take complex dot beta integral of m and foo plus 1, it equals this sum. So when I'm here, if I have natural numbers, m and n, foo plus 1, range. Oh no, it should be like m, sorry, m, 1 is less than or equal to m, and then foo has no conditions on it. Okay, clearly if I just write foo, the autocomplete will complete it in the right way. So it should be like foo. We should know that these are in fact natural numbers. We should know that that is true. This is a vacuous statement. This looks more like what I was supposed to have. So I believe this is sorry. And maybe the point is that this should all be like proved by exact question mark. So exact question mark. And you didn't manage to prove it because this is not supposed to involve the proof of BEQ. So I think that that's fine. So what? Extract goal. Maybe this is what I should have done from the beginning. This is the goal that I want. I don't care about this. M foo, 1 less than m. I don't need this. Wait, okay, is the problem that I had this weird vacuous thing? Yeah, okay, great. So I was up here. The point is that this is supposed to be proved by the binomial formula. But the question, the question in my mind was like, is there actually an easier way of proving this, right? The point is that this is true, and it comes out to this sum. So it's like this alternating sum of binomial coefficients, right? So if I have m plus k, I'm just trying to see if like I can, if I directly substitute beta integral m, if I directly substitute this for this, and I like multiply through, so I get the like, can I prove this question? Can I prove this directly? Question. Can I prove the sum formula directly from the other binomial form? So the question in my mind is like, can I prove that like this? Can I prove this directly? I don't know like why I shouldn't be able to. like it would seem like there would probably be some sort of like formula or fact about this, right? So the point is that this would follow from if I say if I say this is equal to 1. I've sort of written it in a weird way here. The fact is it's m times the choose, 1 over m times the choose. So yeah. So the thing is that it would be something like, if I'm multiplying through, it would be like times this times m times this fraction. So this is all of it collected together. And is there some expression for like products of these things? Like if I expand out, so what is this? This is n minus m factorial divided by k factorial, like quantity k factorial, exclamation point, times n minus m minus k factorial. And n choose m becomes n factorial over m factorial, n minus m factorial. So that's what that becomes. And then this, maybe I can reduce, because the point is I divide by n minus m factorial here, so I can get rid of that, and I can get rid of this. And so now I have something slightly simpler. Yeah, and if I rewrite, like we sort of have a trinomial coefficient here. I think, oops, this becomes this, and I additionally add the m factorial here. Right, yeah, so this is interesting, right? It's n factorial over k factorial, m factorial, and n minus m minus k factorial. So this is like a trinomial coefficient. So it's a sum over trinomial coefficients of this weird alternating thing. And I have an m here, so I could technically go down to m minus 1. Yeah, I mean, so the sum over trinomial coefficients. But the other part of the issue is that it's still only a one-dimensional sum here. So clearly something's not right. Like I was thinking, oh, okay, so maybe there's some way of putting all of this into a trinomial expansion. Maybe there is. Maybe the point is that I put it into a trinomial expansion with like one of the terms equal to 0 or something crazy like that. K goes from 0 to n minus m, right? I mean, the other thing that I can do here is I can delete the m and change this into m minus 1. I'm not sure what that gets me. Yeah, I don't know. This might be a dead end, or I just don't know enough random combinatorics tricks to know the right way of doing this. It sort of feels like there's something there where I could come up with a really clever example of a trinomial coefficient, and then I could argue that it's like a zero polynomial or something. Interesting. Mm-hmm. Yeah, interesting. Anyway, so I guess I should just because I don't know how to do this, I should probably see if I can do it this way. This way. Of course, the thing that makes me nervous about this is that, okay, I'm about to have to use some clever tricks about transposing integrals with sums, and that's always something where it's okay, you have to know the proper 18th century theorem or 17th or 19th century theorem to get the right to prove that you're able to do this transposition. So I think, well, I could at least attempt it, right? So okay, where was the thing that I was, okay, is it this one? Yeah, this one. So the point is that it's this one. And in some sense, so the proof I'm following is here, right? So I should do something like this, where I have this, sorry, where was I? So, or like this, there. Yeah, so this is the proof, and the structure of the proof suggests that I should be proving it using some kind of calc block. So clearly foo is equal to, if it's beta integral of m and n minus, so clearly foo is equal to n minus m here. Yeah, as always, yeah, foo equals n minus m. Okay, I have some spam notification. Okay, so yeah, calc block, calc. So I start with this, and then I unfold. Again, clearly I can't do something that fancy, right? I'm going to actually have to write down something. So clearly this is equal to this. So, sorry. Yeah, m foo plus 1. So it's m, and foo plus 1 minus 1 is just foo. I fold beta integral ruffle. This equals this. colon equals by, sorry, maybe. Okay, but yeah, so I actually have to like produce proofs here. So let's see how it goes, right? I have this. This is this. Can I just like simp maybe? Okay, I simped, but there's still unsolved goals. Is this not now? Let me see. X a real from 0 to 1. X a real from 0 to 1. X cast to a complex to the power m minus 1. S x cast to a complex power m minus 1. Okay, is this a natural power versus this being a complex power? Yeah. Okay, so probably the last thing that I have to do is to say something like, if I take a complex power to a natural power, that's the same as taking the complex power to the cast of the natural power to the complex. Wait, is that even true? Oh no. No. That's got to be true, right? Yeah, that's got to be true because I can take complex powers of negative number. Yeah, that should be fine, I think. Yeah. So the point is that I have an example where if I have x a complex number and n a natural number, then x to the power n is equal to x to the power of n colon c by exact. Complex C pound nat cast, wonderful. So, and just to make sure, oh, okay, so it's actually going the other way. So I think I want to go in reverse then. Oops, complex C pound nat cast. Where am I? No, sorry, here. So put this going backwards maybe. Okay, and now I simply push cast using the fact that m is positive. Oh, wait, what? No, there's more? Okay. And apparently, yes, the last thing is that pushcast apparently doesn't like do ruffles, so this is just ruffle. Okay. Yeah, like every other like tactic seems to like, if it finds that things are equal, it seems to like be like, oh, things are equal. Time to finish the proof. But not pushcast. Okay, so now I have this in this form, which is great because these are natural numbers, right? And here's the part where I want to do something like, maybe calc is not the best way of doing this. Oof, that's right. Like, so here's the issue with calc is like I instantly like the thing I don't like about calc is I feel like I always have to be like rewriting, copying and pasting tons of expressions. The point is that I simply now want to, so let's comment this out. So like I can do all of these actions here. So these are C's. No, that's not exactly what I want. I don't want that. Okay. Clearly, yeah. So clearly there's no getting around the calc block. Okay, so I have a calc block, and this happily gets me into the land of natural numbers. The next step is to get from the land of natural numbers to doing this choose thing. So clearly I copy this by sorry. Okay, and clearly I can like do a bunch of copies like this. Don't know how to synthesize the placeholder. Oh no. So the synthesizer or the placeholder I want to synthesize is I want to take this and I want to write that. Now I have foo. And now I want to use the binomial theorem. So the point is that I want to say something like this becomes the sum from k, for k. So I guess it's k, right? Sum from k in finset.range foo plus 1 in finset.range foo plus 1 of, I don't get why it tries to complete a proof even when I have like a bunch of sorries everywhere. It's like you see that a sorry immediately falls it, so can you just like try and mimic what's already there? -1, a complex number to the power k, foo, sorry, n minus m, which is foo, choose k, c or x to the k by sorry. Yeah, so I think this is right. So this is going to be something like conger, and that gets me to the point conger x, and I can continue with the conger, right? Conger, and now I want to do the binomial theorem. Yeah, okay. What is the binomial theorem? Binomial theorem. Add power. Yeah. Okay. This is hilarious. I should remember that like nat.addPow is like the binomial theorem. Okay, nat.addPow. Unknown constant nat.addPow. Is there no nat? Wait just a second. Did not find an occurrence of this pattern. Okay. Subpow? Do we have subpow? Wonderful. Just a sec. What happened here? I have -1 to the m plus foo, right? -1. Okay, so yeah, clearly it makes sense that that should happen. That something should happen. Foo choose m. Foo choose k. So m equals k. So I think I need to just like conger again, x to k, and then do something like ring or something. K, right. So I have 1 to the k. Simp, maybe simplify. So I had add pow, so I know I want to do like rewrite pow add to pow add. So I have -1 to the k. I have -1 to the k over here. I have -1 to the foo here. Foo minus k. Of course, foo is greater than k. Oops, wait, just a sec. I should have done something differently. Clearly, conger is not sufficient because I actually need the theorem that m is less than foo plus 1. Right. Sum equals. Apply sum, finset sum equals. Oh, but what is the... I know it's somewhere around here. Prod equals, oh, sum conger. Yeah, sure, I bet it's sum conger. Apply sum conger. Yeah, and so now I can intro KHK, and I can have the claim that I need, yeah. And I can do pow add, and I can do some simplification. All right, let's see. Okay, well, I've been at this almost 2.5 hours, so I might have to cut myself off here just so that I don't spend too long on this. But I guess we're finally making progress on this this lemma here. We have not quite gotten to the part where we have to transpose the integral and the sum. Hopefully that's not too hard. But yeah, so I suppose stay tuned. All right, let's stop the stream here.